start with behavior. The reference table we made looks a lot like this, because this is the thing from our textbook. If you have the purple back the softcover student journal, there's probably an image in there that looks like this, and you could rip it out and refer back to it. We're going to use this a lot. I know my face is covering up this one part, but I uploaded this into the Teams page where I put the link to the YouTube video. So you have access to this in behavior chart. Okay, and we also wrote it down on Tuesday. Okay. The top has all degree odd things. The bottom has all degree even. And then the left column of the two pieces of this piece here and this piece here are positive leading coefficients, and the right side is negative leading coefficients. The table is going to be really useful for recognizing the end behavior. And the way that we describe the end behavior is with these statements here. So we'll go into that for just a second, but I want you to see what's happening with the graphs before I do some examples of what we do with this table. Okay, so I'm going to go on Desmos. We're going to get rid of this thing. And we're just going to make up some functions. So x to the fourth minus 3x cubed, maybe plus x squared. Whoop. Minus 4. Let's make this 2. Meh, it's fine how it was. Okay, this is an x to the fourth function. It's a quartic function, I think. And you'll notice it has an even degree. So this part right here is the degree. The exponent is even. And so the degree is even. And the leading coefficient, the number in front of this x to the fourth, because it's written in standard form, is positive. So if we were to look at our chart, our in behavior chart, we have an even degree here and a positive leading coefficient. So the end behavior, the ends of the graph, the extremes of the graph, are going to follow these instructions. But let's look at this graph better. What we really care about is the ends. So this piece here and this piece here. I'm going to zoom out a bunch, but you can think I've covered up the squiggly kind of interesting looking bit, right, with my face. It's behind me now. We don't care about that part yet. We will eventually, and we'll talk about it. But for now, we only care about the very extreme ends of the graph. So if I zoom out, notice how it kind of just turns into a line. But there's a gap here. It's just going to keep going up forever. What we're saying is if we go infinitely far to the right, the graph is infinitely positive. It's just going to keep going up. It's not ever going to come back down. If we go infinitely far to the left, if we put in really big negative numbers for x, the graph's just still going to go positive. Okay? And that's what that chart tells us. All right, and we could change these values. So let's zoom back into something reasonable. And if I change this to an odd number, instead of a 4, I make it like a 7. So I've got an interesting squiggly bit here. But if I cover that up, like with my hand or something, and I just look at the extremes, now the odd function, one side goes up and one side goes down. They go in opposite directions. That's because when we're multiplying by an odd number of things, when we have negatives, we're going to get a negative. So it doesn't matter if this is a 7 or a 5 or a 3 or even, I don't know, a 9. Let's go back to 7. All of those have one side that goes up and one side that goes the opposite direction. Okay, so this on our chart has a positive leading coefficient and an odd degree. We have a positive leading coefficient, and odd degree means it goes up to the right and down to the left, which is what this notation says here, and we'll talk about that more in a second. Okay, so we're using the chart to describe what the ends of the graph look like. What does that look like in practice, in an example? So the problems are going to look like this. They're going to say describe the end behavior of the graph. End being the extremes, the left and the right, and behavior just being like, what does the graph actually do? Okay, so he'll be given a function. It'll probably be in standard form already. F of x here equals negative 0.5x to the fourth plus 2.5x squared plus an x minus a 1. Most of this information for describing the end behavior does not matter. The only thing that we care about is this part, that first term. The first term. Okay, so we're going to need to identify what is the degree and what is the leading coefficient. So what's the degree and what's the leading coefficient? What's the number in front? Okay, so here, the degree, we don't care about this stuff. The degree is just the biggest exponent. It's 4. Is that number even or odd? Well, 4 is even. So we have an even degree. It's x to the fourth. Okay, and then what's the leading coefficient? What's the number in front of this x to the fourth? Well, it's negative 0.5. We don't care so much about what the value is. We just want to know, is it positive or negative? Well, this is negative. And here's why we don't care about what the numbers actually are. Imagine that we're substituting in a really big number for x, like a million. A million's a pretty big number. Might be more money than I ever see in my lifetime, kind of thing, kind of number, right? We can imagine a million, kind of, but it's big. If I put a million in here and I multiply it times itself 4 times, so I raise a million to the fourth, I'm going to get a huge number. But if I put a million in for x squared, I'm not going to get nearly as big as this x to the fourth. Right? Even if it was 100, it's not going to get as close. And just a single x here, just a single a million, is not going to be as close as a million times a million times a million times a million. That's a lot of zeros. Okay. So this x to the fourth, the biggest exponent, controls the extremes of the graph. Now, yeah, squiggly things are going to happen in the middle. We don't care about that. We just care about the extremes. So as we go really far to the right on our graph, does the graph go up? Does it get bigger? Or does it go down? Does it become negative? Well, positive or even. So they're going to go in the same direction on both sides of the graph. But as we go really far to the right, we get a really big number, but we multiplied it by a negative. It doesn't matter that this is a half. Half of 4 million is still a couple million. It's still big. So we can think, okay, without graphing any specifics, I know as I go to the right, the graph is going to end up going down. And as I go to the left, the graph is going to end up going down. And we don't care yet about all the middle stuff. We will, eventually. We'll figure that out. But for now, it doesn't matter. We just want to know, what's the end behavior? What is the edges? Okay. And so our answer is not this graph. Our answer is math language to describe what happens as we go to the right and as we go to the left. So what we write as x approaches, this little arrow means approaches, as x goes to positive infinity. This just means as we go to the right on our graph. As we go to the right, does the graph go up or down? Does the outputs of our function, f of x, do they become big positive numbers or big negative numbers? Well, f of x is going to approach negative infinity. As I go to the right, the graph goes down because this number is negative. And you can think this through each step, or you can just check on your chart. We need an even and we need a negative. Well, that's this quadrant, the bottom right one. And so we're writing these things here. As x goes to positive infinity, the function goes to negative infinity. As x goes to negative, as we go left, negative infinity, we're still going down. So that's half of it. Then we would also say as x goes to the left, as x goes to negative infinity, then the function, the output, f of x, approaches negative infinity. Well, it goes down on both sides of the graph. Okay, so you can use that in behavior reference that we drew on Tuesday, or you can logically think through what is the graph going to look like. But our answer is this thing. We good so far? Any questions? Okay. Let's do another one. X to the fifth, 1/3 x to the fifth plus x squared minus x minus 18. So again, we only care about the degree and the leading coefficient. This other stuff on over here changes the shape of the graph and the curves, but it really doesn't impact the extremes. When we put really big numbers in here, this is the thing that's going to be in control. So the degree is 5, which is an odd number. So the biggest exponent's 5 here, which is odd. And then the leading coefficient is 1/3, which is a positive number. Doesn't matter that it's a fraction. You know, when I put 1,000,000 in for x, or as I approach infinity, that one dividing infinity by 1/3, it's still infinity. Still really big. So this graph, the ends, I don't know what it looks like in the middle. It doesn't matter. It might actually go up and down like that. Probably not that many times because it's only to the 5th power. But as I go to the right, as I put in really big numbers here, I'm going to get really big positive numbers. It's going to go this way. And as I put in negative numbers, because this is an odd number multiplication, we're going to get a negative number. So it's going to go down that way. And then that's the extremes on the inside. Who knows what happens? We'll figure that out later. Okay. So our answer is as x goes to the right, as x approaches positive infinity, as we go to the right on our graph, what does the function look like? What does the output look like? Well, it goes up, which means it also goes to positive infinity. As x goes to the left, as we go left, the function's going to go down. It's going to go down. It's going to go in both directions. And so all of these are going to have the first half the same, right? It's always going to be x approaches positive infinity, x approaches negative infinity. The only thing that's going to change is the output, right? We're always going to check left and right, but we just want to know which direction does it go. Okay, so we can use that chart that we made to reference what the directions are, what the notation is. Any questions? We good? Okay, so that's in behavior. You can always check it by you can plug this into Desmos, see what the graph looks like if you want. And say, okay, as I go to the right on the graph, is the graph going up or is it going down? Should this be a negative infinity? Or as I go left, does the graph go up or does it go down? Okay. So that's kind of a continuation of what we talked about on Tuesday. We didn't really go in depth with it or do any examples. We just drew the chart. So now we're going to talk about evaluating. I know I'm not on the screen yet. Evaluating. This is like the warm-up problem we did. Just a pre-check. Evaluating is substitution and simplifying. We're going to substitute a value into our function, and then we're going to simplify it. So we're going to get rid of all the variables because we're going to put a number in, and we're going to simplify it until we have a single number left. And this, you've done this before, but probably not on the scale we're going to do it. So we're going to have lots of terms, or a few terms, that we need to substitute into and simplify. So evaluate f of x equals 2x to the fourth minus 8x squared plus 5x minus 7. When, so it's always going to give you the value for x. So when x equals 3. This is when x equals 3. So to substitute, there's a couple ways to write this notation, but function notation, which is what this is in, this is the function named f where x is our variable. Well, we're saying when x is 3, so we would say f, the function of 3. And so then where all of the x's are, we're going to substitute in the 3. So all of these are going to get a 3. All those parentheses. So we did the first part. We substituted. Now we just need to simplify this. There are no variables here. And so we can use GEMS or PEMDAS to simplify. When we simplify, we go down. Start at the top, we go down. So we say grouping symbols, that's parentheses, brackets first. Then we do the exponents, then we multiply, then we add and subtract. So we got to do our exponents first. So this equals 2. I'm going to keep everything in parentheses so we can see where the multiplication happens. But 3 to the 4th is going to be 3 times a 3, which is 9, times a 3, which is 27, times a 3, which is 81. You can use a calculator to do this. Okay. If you don't know 3 to the 4th off the top of your head, either multiply it out, write it down, or use a calculator, or do it in your head. Okay, then it's going to be 3 squared, which is a 9, plus, normally I would just write 15 here, because it's 5 times 3, but I want to show all the steps happening at the same time. So we've gotten rid of the exponents. Now we're going to multiply. So this was we did exponent step. Now we're going to do some multiplication. So 2 times 81, which is 162. 8 times 9 is 72. 5 times 3 is 15, minus a 7. And here, now, we did the multiplication. You can use a calculator here, too. 2 times 81, I don't expect you to know that off the top of your head. So you could use a calculator, or you could just do 2 times 8 is 16, and 2 times 1 is 2. Okay, so now we're going to add and subtract. My suggestion is do this in multiple steps, I would not try to keep track of all these numbers in my head at once. So I'm going to do this chunk and then this chunk. And on the next one, I'll show you another strategy. But so 162 minus 72, the 2's are going to cancel. And so it's 160 minus 70, which is 16 minus 9. So this is 90 plus 15 minus 7, which is 8. And so we get 98. Excuse me. Any questions on what we did there? I had someone say this looks complicated, but isn't. I don't know about that. It might be complicated. But here's the thing. Each step is just a single thing, right? We simplified the exponent, got 81. We multiplied, and then we subtracted. The real issue here is that we're doing it many times. Okay? So don't try and keep a bunch of numbers in your head. Leverage the paper to write out all the steps. Because there's a lot of things, like if you mess up, one addition, multiplication, yeah, Evelyn, this is basically what we're doing today. One multiplication, then, this might not end up being 72, and then we'd get the wrong 98 down here. Okay. So let's do one more of these, unless we have any questions on it. Okay. We're going to evaluate. Here, f of x is equal to negative 3x to the 5th plus x to the 4th minus 2x squared plus 10x minus 5. And then we have a semicolon. X is negative 2. This is saying the same thing. We want to know what this function is when x is negative 2. I just haven't written the when. This is a common thing to put with mathematics, to put a semicolon there to do shorthand. But we're still basically doing f of negative 2. So I'm going to go through all of where all the x's are, and we're putting a negative 2 there. Negative 3 parentheses to the 5th plus parentheses to the 4th minus 2 times 3 squared plus 10 times parentheses minus 5. There are a lot of terms. So make sure when you're copying the problem down or writing out all the numbers that you're going piece by piece to not drop any like negatives and positives or mix up the exponents or something. Put negative 2 in here, negative 2, negative 2, negative 2. Parentheses are really important, especially with the negatives, because this is not minus 2 to the 4th. It's plus negative 2 to the 4th. This is going to become a positive number. So when we do GEMS or PEMDAS, PEMDAS is the same. We're going to do parentheses and exponents first. Grouping symbols and exponents are going to happen first here. And so my exponents are going to become negative 3 times 2 to the 5th. 4 times 4 times 2, 16 times 2 is 32, and it's negative. So I very quickly multiplied 2 to the 5th in my head, but we're doing 2 times 2 times 2 times 2 times 2, 5 2's being multiplied. And since there's an odd number, we're going to get a negative number out of it. Plus negative 2 to the 4th is 16. minus 2 times 4. Negative 2 squared is 4. Normally, I would just write minus 20. I'm trying to show all the pieces. Okay, so we simplified our exponent. And now we're going to multiply. And if you need a calculator, it's okay. Just be sure you're keeping track of the negatives and using parentheses in correct places. We're going to multiply 3 times 32. It's a negative times a negative, so this is just going to be a positive number. The key here being, if you want to do this in your head, just do 3 times 3 is 9, and 3 times 2 is 6, and you get 96. Or use a calculator. Or use, long multiplication or some other tool. Plus 16, minus an 8, minus a 20, minus a 5. So this is the other strategy. So we've multiplied all the numbers out. Some of them are pretty simple, right? 2 times 4 is 8. Make sure you keep the negative. 10 times 2 is 20. Make sure you keep the negative. Got a negative 5 at the end. Now we just need to add and subtract. And here we can just keep the positive numbers together and the negatives numbers together. So 96 plus 16 is going to be 100 plus 12, which is 112, minus all these numbers combined give us negative 33. So 112 minus 33, you can use a calculator or do 82 minus 3, so 79. 79. Okay, and so we've substituted the negative 2 into the problem where all the x's are. That's what f of negative 2 means. And then we use gems or PEMDAS to simplify, do the exponents first, then multiply, then add and subtract, and then we get our value. And this basically gives us a coordinate point on the graph. This gives us negative 2, 79, which that point might not be super helpful, but other points might be if we were needing to graph or something like that. Okay, and so that is end behavior and evaluating polynomials.